Greetings everyone, welcome back to Calc 2. It's time to continue in this second unit when we're talking about sequences and now series. Basic definition of a series is when you have a sequence like we just talked about in the last lecture, but instead of just listing the sequence, you are actually summing up all of the terms in the sequence. Okay, so if I can list some sequence, for example, like n over n plus 1, that sequence is 0, 1/2, 2/3, and this is A0, A1, A2, A3, so on and so on. Right? This is when n is 0, this is when n is 1, this is when n is 2, this is when n is 3, and this is when n is some value k. So that's a sequence, like we've just talked about. A series is when I can take the sum of these. So here's the sequence, here's the series. The series is going to be the difference in whether I write this sigma in front of the sequence listing. So I've got the generic listing the same, n over n plus 1, as you can see. Here, though, it's like I'm listing an individual a sub n, like it's a single term for the nth term. Whereas here, I'm telling n to keep flowing from 0 up to some value k, and the sigma means to sum them up, just like it did back in Calc 1 when we first started talking about the sigma notation that we use to do integrals. I'm not doing an integral here. This is just telling me that I want to add up all of the terms where n starts counting at 0 and counts all the way up to the value of k. And then this is the calculation for each step. So this is the same sequence, 0, 1/2, 2/3, 3/4, da 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 da, all the way up to k over k plus 1, except instead of listing them, you can see I'm summing them up. I'm adding up all of the terms. That's what a series is. A series is just when I add up all of the terms in a sequence. Okay, now an infinite series is whenever I use an infinite sequence to sum up. So basically I'm letting the k value here go to infinity. So I have the summation n equals 0 to infinity of n over n plus 1 would just be 0 plus 1/2 plus 2/3 plus 3/4, so on and so on and so on. It would go to infinity. Okay, so then you get into a complicated school of thought just by looking at the definition of what this is trying to say. Are we really trying to add an infinite list of numbers? And how can you even possibly imagine doing that? And then we get into the whole talk about what does it mean to converge and what does it mean to diverge again, just like we did back with sequences, and even before that we were talking about integrals that diverged because they were infinite in size or undefined. Okay, so more of that same language here. But before we even get to that, what does it even mean to add up an infinite list of numbers? And is that even possible? So instead of looking at it like this, we've chosen to define a series slightly differently so that I can apply a topic that we've already discussed. Okay? So what we do is we define something called a partial sum. A partial sum is when you have an infinite series and you want to add up an infinite list of numbers, but a partial sum is when you only take the first 2 or the first 3 or the first 5 of the series and just add those up. Okay? So then the full series, an infinite series, can be thought of as a sequence of those partial sums. Okay? So, for example, if capital A was the sum of some sequence A sub n, okay, then the partial sum A sub k, notice this is capital A, where I'm using capital A to represent the entire series, then a partial sum is that capital A where I've picked some number to stop adding. Okay? And then would just go all the way up in the sequence up to that value. So it's not the full infinite series, it's a partial piece of it, the front end of it, not the infinite tail. Okay, so here's an actual example using that same series that we were just talking about. If I define capital A to be the series where n is summed from 0 to infinity of n over n plus 1, then I'm adding the values 0, plus 1/2, plus 2/3, plus 3/4 as n gets bigger, right? N equals 0, n equals 1, n equals 2, n equals 3, and so on and so on. Then these would be considered the partial sums right here. A sub 0 would be just 0. A sub 1 would be A0 and A1 because it's a partial sum. I go up to the one numbered term. A sub 2, I add up to the two numbered term. So that's 0 plus 1/2 plus 2/3. A sub 3 would be A0, A1, A2, and A3 added up. And notice that's it. That's where it stops. It's a partial sum. Okay? So the infinite series, the whole thing that goes on forever, is a sequence now. What is it a sequence of? It's a sequence where these partial sums keep adding on one more term as it goes down and further and further. So then what I can do is treat this like a sequence. But the way that I form the sequence is by actually adding these up and getting these sum values. And then once I have those listed out values, I can attempt to take a limit of those, just like we did with sequences in the last lecture. Once I have it listed out as a sequence, I can take a limit of it, and if that limit exists, right, well, then the limit can be convergent. Or if the limit doesn't exist or is an infinite limit, then it can be a divergent limit, right, a divergent sequence. Once I've identified the sequence by using these partial sums, I can think of this infinite sum, this one infinite sum, like a pattern of this progression here. And then I can use that progression in a limit to predict if it converges or diverges. So rather than think of this as just, hey, I'm going to add up an infinite number of numbers, we're going to use the same school of thought that we've been using since the beginning of Calc 1. We use patterns with limits to figure out these unbounded lists of things. Okay? Now the sum may not be unbounded, but the fact that the list is infinite is what I mean. The counting is unbounded. Okay? Some of these will be convergent, even though I'm adding up an infinite list of numbers, if you will. Okay? It can still be written as a sequence that is convergent. It does actually stop and converge on a finite number. And then there will be others that don't. They'll diverge. And that's the beginning of what we want to talk about in this lecture video. And then every other lecture video for several more after this one, we'll be talking about the different tests that we use for different types of infinite series that fall into certain categories. And mostly we're interested in just a yes or no. Does it converge or not? A lot of these things, it's very difficult to determine the exact value of what they converge to. We'll talk about some of the ones that we can easily find the actual sum that these infinite sums are. And there will be other ones where it's too complicated, and even just one of these series could be one person's lifelong career to figure out the pattern of how to find the exact value of a sum, an infinite sum. Okay? So we'll be talking over the next several videos, like I said, about the different tests and whether or not things converge. That's our main goal for right now, to focus on, can I get an infinite series to converge or does it diverge? So let's get some examples of the basic idea of how we're going to approach series just from the definition side. And then I'll start to show you special cases, and then through the next few lecture videos we'll build the other methods that will solidify most of the series that will encompass your mathematical career. So let's start with the sum where n goes from 2 to 5 of 1 minus n over n plus 3. I hope that you'll realize right away that this is not an infinite series. I just wanted to throw this example in there to make sure that you're paying attention to the boundaries of your counting variable. The counting variable, of course, is n in this case, and it is counting from 2 to 5, which is finite, not infinite. And as long as the individual terms of a finite series are themselves finite, then this is always going to converge. Okay, as long as each individual term is not unbounded, right? Each term is an actual finite number, then this is going to converge. I have this already punched out. This is going to be negative 1/5 plus negative 1/3 plus negative 3/7 plus negative 1/2 for a final result of negative 307 over 210. Okay, so this one, it's obviously finite simply because it's not infinite, right? Each individual term is finite, and there's only a finite number of them. Next, a pretty straightforward sequence that we've seen before, now turned into a series. And if you recall, the sequence itself did not converge. So the series may or may not have, you can see for yourself here. So look, let's write down just the sequence first. The sequence, okay? The sequence is, if I plug in 0, negative 1 to the 0 is 1. If I plug in 1, I get negative 1. If I plug in 2, I get 1. If I plug in 3, I get negative 1. So you can see the pattern here. There's my sequence. So it just alternates between 1 and negative 1. The sequence itself does not converge. Okay, it's not infinite, but it's not monotonic. It sticks between the 1 and negative 1 constantly. So then, right here, I've got I'll make a sequence of the partial sums. Okay, so then a sub 0 is just the 1 that you see here. A sub 1 is going to be 1 plus negative 1, the first two terms added together, which is going to be 0. So far, this is my partial sum sequence, 1, 0. A2 is 1 plus negative 1 plus 1, which you'll see is 1 again. I'm hoping that you're seeing a pattern forming here. A3 is 1 plus negative 1 plus 1 plus negative 1, which is back to 0 again. And if you're guessing that the next A4 should be 1, you're not wrong. It's going to keep alternating like this. Okay? So now think of this like a sequence. This does go on forever. It's an infinite series, but I've turned that infinite series into a sequence of partial sums. And if I let that sequence go to infinity, it's an undefined limit. It's not unbounded, it's not infinite, it's an undefined limit. You simply keep bouncing between 1 and 0, 1 and 0 for the sum of these things. Okay? So the limit here is undefined. The limit of a sub k as k goes to infinity is undefined. So this diverges. All right. The sum of all the terms where n counts from 0 to infinity of n over n plus 1. And this is the series that I was talking about in the last scene. Let's actually go ahead and write out the sequence, and then let's turn that sequence into partial sums, which will give me a sequence equivalent to my series, right? So here's my sequence, right? My sequence is going to be 0, 1/2, 2/3, 3/4, 4/5, 5/6, 6/7, 7/8. That's the sequence. Okay, so now let's do partial sums. My first partial sum, a sub 0, is going to be 0. Next, a sub 1 is 0 plus 1/2, right? The first two terms there, which is going to give me 1/2. A sub 2 is going to be 0 plus 1/2 plus 1/3. Let's go ahead and keep this thing rolling faster so I don't have to run this out. We have 7/6. A3 is going to be that same 7/6. I'm just going to start carrying it. Plus, oh, I'm sorry, that wasn't 1/3. This should be 2/3. My bad. That's 7/6. That's more like it, yeah. Yeah. Okay, so then this 7/6 counts for these three, plus the 3/4. Right? That gives me 23 over 12. A4 is then the 23 over 12 that we have here, right? That represents these first four terms here, plus 4/5. Okay? And that gives me 163 over 60. A5 is that the first 0, 1/2, 2/3, 3/4, 4/5. That's this, plus the 5/6, which is then going to give me 71 over 20. And I'll go one more. Let's go one more. The 71 over 20, which is the first 0 to 5 terms, then plus the 6/7. Okay, that's going to give me 617 over 140. Okay. Now you may not, see a lot of information here. Instead, let's convert these into mixed numbers so you can start to get the feeling here, right? Or even, besides mixed numbers, let's just go ahead and bounce these into decimal. Of course, I have 0 for 0. 1/2 is 0.5. 7/6 is 1 and 1/6. So that's 1.16 continuous. That's 6, right? Keeps going. 23 over 12 is going to be almost as big as 2. So I have 1.91 continuous 6. 163 over 60 is 2.71 continuous 6. 71 over 20 is 3.55 even. That's nice. 617 over 140 is 4.0714. You know what? I'm going to go ahead and just start with the approximate symbols there, because I'm just going to chop it right at the 3 right here. Okay, so let's look at the pattern that we've got here. I've only gotten up to the 6th partial sum, which means I've added up from 0 up to 6/7, right? A0 A1, A2, A3, A4, right? A5, and then A6 is the 0 to 6 terms there. And we've added all those up. Okay, so let's look at the pattern and then jump to what we think the limit of these A sub k's would be, right? That's what we're trying to build to here. What do we think the limit as k goes to infinity of the partial sum A sub k is going to be? Well, it starts with 0, 1/2, and then we kind of stick around in the ones for a little while, and then we scoot on to 2, then 3, then 4. I mean, I'm hoping you're seeing that this pattern, it's not really getting close to anything, okay? And it's getting like an increasing size going on here, right? It's getting faster even. Well, not faster, but it is gaining 1 every time, okay? And that should sort of make sense to you also. Notice the further this thing goes, okay? 2/3, 3/4, 4/5, 5/6. Just the sequence itself has a limit of 1, okay? So keep that in mind. This is going to become important in a little bit. I'm going to show you a very basic idea in a little bit. The limit, just as n goes to infinity, of n over n plus 1 is 1. So my size of my sequence pieces here is increasing to 1. So imagine adding an infinite number of 1s. It would be unbounded. And you'll notice that's kind of what starts happening, right? I kind of stick around in the 1s for a little while, but then this thing keeps going up a whole number almost. Well, I mean, it's not a whole number actually, because it's a little bit less than 1. But you see what I'm saying? We're gaining large chunks every time. This is definitely unbounded growth, okay? So this limit of the partial sums is infinite. The partial sums going all the way to the actual infinite sum is going to be unbounded. So this one definitely, this series right here, this series diverges. Okay. Next, I have this sum from n equals 1 to infinity of 1 over n times n plus 2. Let's start like we did before. Let's write down the sequence here, right? My sequence is going to be 1 over 3, then 1 over 8. And I'm just doing a pattern here, right? It's 1 times 3, 2 times 4, then 3 times 5, 1 over 15, and then 4 times 6 is 1 over 24. Then I've got 1 over 35, 1 over 48. 6 times 8 would then be 7 times 9. Then 8 times 10, so on and so on. I'm going to go ahead and spoil the beans on this one. This one does converge, okay? I want you to notice, first of all, the limit of the sequence. And again, we're going to talk about this limiting piece of the sequence in a minute. This is not, I do need to emphasize, this is by no means a guarantee. So don't totally look for patterns here, but I do want you to see that the limit of just the sequence itself here goes to 0. In other words, it keeps shrinking. And I'm hoping you're noticing that just from the sequence here. As this denominator grows, the actual size of these fractions decreases. Okay? As we're going to see in a minute, that's really the only way you can expect an infinite series to eventually converge. It has to quit adding at some point, even though it's an infinite list. At some point at the tail end of that infinite list, it has to go to nothing. Like, okay, I'm adding a number, but I'm not really adding any size anymore. That has to happen, or else it's just going to be unbounded like this one. Okay? By no means is this a guarantee, though, that it converges, and we'll discuss that in more detail in a minute. Okay? But it is important to note that the limit of the sequence does go to 0. Okay? Let's look at a few terms of the partial sum. Obviously, A0 is 1/3. A1 is going to be 1/3 plus 1/8, which we have 11/24, right? A2 is going to be the 1/3, the 1/8, and 1/15. And then that's going to give me 21/40. A3 is all of that plus the 1/24. Okay, which we get 17/30. A4. Oh, you know what? I made a boo-boo. Boo-boo, guys. I counted wrong. This should be A1. This should be A2. This should be A3. This should be A4. And this next one I'm about to write should be A5. Pay close attention, and obviously I'm hoping that you're hey, Professor Simon, you messed up too. See, this one started with 0. So I started with A sub 0. This one starts with 1. So I should have started with the first partial sum where n equals 1, right? Or k equals 1. A5, right, is going to be that 17/30 plus the 1/35. Okay? Which I get 25/42. Okay, so let's start looking at what some of these values are, right? Obviously, 1/3 is equal to 0. Continuous 3. 11/24 is 0.458 continuous 3. 21/40, 0.525. Next, 17/30 is 0.5 continuous 6. 25/42 is 0.5952, and that's where I have to start throwing in the approximate symbols. Okay, so from here, I'm just going to start making big jumps. Okay, A sub 8 is going to be equal to 29/45. Now remember, A sub 8 means that I'm adding up the first 8 terms, right? So 1, 2, 3, 4, 5, 6, 7, 8. If I add up all of these only and stop right here, that's A sub 8. Okay? I get 29/45, which is equal to 0.64 continuous there. Okay? So I'm going to go a little further in just a second, but I just want you to notice where we're at with this particular sequence of partial sums. It started out growing pretty good, 0.3, 0.4, 0.5, but notice it starts slowing down, 0.5, 0.59, 0.6, and then this is even a bigger jump, right? From A5 to A8 before it passed up the 0.6. Okay? Now let me list out some of the more extreme values here. A20 is approximately 0.703. A50 is approximately 0.731, and A100 is approximately equal to 0.7 401. Let me go ahead and list one more. A1000 is approximately equal to 0.749001. Okay. So we went pretty extreme on that one. I actually found a pattern for adding up to the 1,000th fraction here on this particular sequence, just so I can make the point of what we're doing here. This is like a brute force limit back from Calc 1, if you have to keep listing out the y values of a function until you finally, see a pattern in it. Okay, so I'm basically brute forcing a limit here, which that's what we need to write out, right? We're interested in what is the limit as k goes to infinity of the partial sums, a sub k. What are my partial sums eventually going to here? Well, as you can see, we've pushed it. I went from 8 to 20, and that jumped me from the 0.6s to the 0.7s. And then I jumped a whole 30 numbers. A50 got me midway of 0.7s. Then I doubled it to 100 and got 0.74. I, tenfolded that one to 1,000, and I got 0.749. Okay, so that's a huge jump to get not very much gain there. You can see this thing is extremely slowing down. It does take a long time for this to converge, but I hope you're noticing that this does converge. And what it converges to is 0.75. It actually converges to 3/4. In the next lecture video, when we talk about something called telescoping series, I'll actually prove to you this series does converge to 3/4, 0.75. Okay? So yes, this is an infinite list of numbers. It is an infinite sequence that if you convert into an infinite series, it converges to the value 0.75 or 3/4. Even though it's an infinite list, this sum equals 3/4. Right? So it converges. So let's take a quick look at those three series that we built from those sequences. The first one was -1 to the n. And remember we showed that our sequence was bouncing between 1 and -1. You can see the green dots. That represents the sequence here. And then I've got the series in red. And I've only got it up to k equals 10 right now. So then as this carries on, right, you can see the way this is going here, that the things are just never converging. You can see they're bouncing between the 0 and the 1 values here. Okay, next we want to take a look at the sequence that was the n over n plus 1. Of course, I have to use x's for my function here. Okay. Okay, so the sequence is in green. And what you're going to notice is that the sequence is going to converge. Let's just look at the sequence itself for the first 164 terms here. You can see very quickly this thing, the sequence adheres to approaching 1. The limit of that one goes to 1. And remember, what that meant was that the series is going to diverge. And sure enough, if you look at the pattern of the series, it very quickly just takes off here, right? Let me shrink this down and you can get an even better view. You can see the series is just taking off to infinity extremely fast, right? I'm out to the 164th term, and it's already way up here. Okay, so let's get this back to scale. And now let's take a look at the 1 over n times n plus 2. Okay? So just the sequence itself, very quickly you can see it approaches 0 here. The sequence converges to 0. And then the series right here, you can see it starts to converge. And if I spread this out a little bit more, and let me just type in a line, y equals 0.75. And you can see that this line is acting like an asymptote to the series. The series is actually converging to 3/4 here. Now I want to talk about expanding the idea that we were exploring when we were talking about the limit of the sequence that a series is built from. It's very important that you don't get this logic mixed up, because the very first test that we use on a series is what I've been always calling the nth term test. Some people call it the divergence test, the nth term divergence test. There's all kinds of names for it. The bottom line is you can use the limit of the sequence that a series is built from to determine if the series is going to diverge. You cannot use the limit of the sequence by itself in general to determine convergence. You can only use it to determine divergence. Let's talk about this for a second. If I have some series, capital A, that is constructed from a sequence a sub n, okay, so I have some series set up such that the partial sums a sub k is made up of the sum of the terms of the sequence a sub n. Okay, right here, if the limit of the sequence does not go to 0, then you can automatically assume, well, it's not just an assumption, it's an actual proof, okay, that the series diverges. And this includes if the limit is completely undefined or if the limit is infinite. If the limit is even just some other number other than 0, it could be -2, it could be 10, it could be 1, it could be 0.005. It doesn't matter. If the limit of the sequence is not 0, then you are guaranteed that the series that it is constructing will diverge. And it's because of the same idea that we were talking about a moment ago. If I'm adding up this long infinite list of numbers, at some point at the tail end on the infinite side, you have to quit adding. It has to be such that the amount that you're adding is shrinking to 0, so that even though it's an infinite list, at the very end of the list, you've stopped adding value to the sum. Okay? So right here, the sequence not going to 0 is saying, well, we're just going to keep adding value forever. And it's just going to keep stacking up. It's going to be unbounded. Okay? This is the divergence test. This is the nth term or the nth term divergence test. This is an actual test that we use to determine if a sequence is divergent. Okay? Now, the converse of the contrapositive, if you will, of this logic is that if a series converges, then the limit of the sequence is 0. And to some lesser extent, there might be some proofs out there in obscurity that do actually use this, because you may be able to find some series that converges and it'll help you show some really weird limit that you couldn't do otherwise is going to 0. Fine. For the most part, we really need to look at whether or not a series is converging or diverging. So this particular version of the logic is not going to help. It will be true if you already know that something converges, then its sequence must have a limit of 0. It's just not going to be very useful to us at this time for the most part. But definitely do realize that this is the way the logic works. Okay? Now here is one of the fallacies of logic that come up all the time with this. Someone comes up to a series and says, hey, the limit of that goes to 0. It definitely converges. False. That is a false use of the logic that goes along with this. Just because the limit of a sequence goes to 0 does not guarantee that this series of adding up all of those sequence terms is going to converge. Okay? It is needed. It is what we call necessary, but not sufficient as far as a proof goes. Okay? And that's actually what we're doing with most of these series. We are actually going to be proving, like a mathematical proof, whether or not the series converges or diverges. We actually are going to write out steps to show 100% followable logic of it is proven this does converge or this does diverge on each of the series that we approach. Okay, so the limit of the sequence going to 0 is what we call necessary but not sufficient for most series. What that means is, yes, it's true. If it's going to converge, the limit of the sequence does need to go to 0. But that is not enough to say it definitely converges. I cannot guarantee that a series will converge just on the limit of the sequence being 0 by itself. Okay? So let's throw out a few examples so that you can see what I mean. We've already talked about these two series in the last scene. The sum of n going 0 to infinity of n over n plus 1 diverges. We already saw that. Because the limit as n goes to infinity of n over n plus 1 is not 0. Remember, we noticed the limit was 1. This is actually good logic. I could actually have used this rule right here to 100% show that that particular series diverged because the limit of the sequence that it's built from was not 0. It was 1. Yes, that is good usage of this logic statement. The other one, the sum as n goes from 1 to infinity of 1 over n times n plus 2 converges because the limit of its sequence is 0. And that particular statement is false, not because this doesn't converge. Yeah, we saw this does converge, but this is not the reason it converges. Okay? That's improper use of the statements that we are building here. I cannot say that the reason that this converges is because of that limit being 0. The limit does need to be 0. Okay? It wouldn't converge without that being true. However, this is not a proof of that. Okay? So this would not be good to write on a test paper. That particular statement. Okay? That is not a strong enough proof. That is not enough evidence to say that a series converges. We have other things for that. And as you saw in the last scene, at the very least, you could, brute force all of the partial sums to get there. Okay? Now here's an actual counterexample which shows that you cannot use the limit of a sequence to prove convergence. Here is a series. It's actually a very important series. It comes up in a lot of different chemistry and physics topics all over the place. Okay? It's called the Harmonic Series. And if you'll notice, the limit as n goes to infinity of 1 over n does go to 0. However, as I'm going to show you here, this series diverges. So even though the limit of the sequence converges to 0, the series itself diverges. And usually the explanation that we throw out, just as the hand-waving argument, is that it the limit of the sequence goes to 0, but not fast enough. So this thing blows up unboundedly because it just doesn't quite hone in on that 0 fast enough, and so it just keeps adding value forever. Okay, here's one way to truly prove it. I found this through several different articles and even in the OpenStax textbook. This is a very common way to show that this particular series diverges. In a few lectures, I'll bring this series up again, and we'll use one of the other more solid methods to 100% show you step-by-step proof, not just a bunch of counting on the numbers here. Okay? So, here's what this series looks like. 1 plus a half plus a third plus a fourth plus a fifth, so on and so on and so on. Right? Group these into groupings that end in a 1 over power of 2. So the 1 doesn't count because that's 2 to the 0 in the bottom. So then I have 1 over 2 to the 1. 4 is 1 over 2 squared. 8, right here, that would be 1 over 2 to the third. So you see the way I grouped it is by ending a group by 1 over a power of 2. And what this does, it allows me to group these things and turn them into halves. So look, I put a greater than sign here because this is what I'm doing. Okay, so you see A1 is 1, that's true. A2 is 1 plus a half, that's definitely still true. Okay, now for the next one, for A sub 4, I'm going to do this grouping. So I've got A3 and A4, like I'm just skipping over A3 and going straight to A4. Okay, for A4, I'm switching to a greater than sign, and that's because what I'm doing is I'm looking at the 1, the 1/2, the 1/3, and the 1/4, and I'm comparing it to the 1, the 1/2, the 1/4, and the 1/4 here. So just for a moment, imagine this isn't here and this isn't here. Okay? So what I'm doing is I'm looking at the fact that 1/3 changes to a 1/4. See, that's the only change from here to here. And 1/3 is greater than 1/4, right? 1/3 has more value than 1/4. So over here, notice 1/4 plus 1/4 is 2/4, which is a half. Okay? So I basically have 1/2 plus 1/2 here. So essentially, the actual value of A4 is greater than this 1 plus 2 times a half. And then I'm going to do that again. I'm going to skip all the way to A8. And then with these 4 right here, again, I'm going to rewrite the 1/5, the 1/6, the 1/7 as 1/8, 1/8, 1/8. And again, 1/5 is greater than 1/8. 1/6 is greater than 1/8. 1/7 is greater than 1/8. But when I write it this way, this is 4/8, which is also 1/2. So you see now why I'm doing it in groups of by power of 2. Every time I group it that way, I'm going to always get something that will add up to a half. So if I go up by powers of 2, right, 1, 2, 4, 8, then I'm going to keep adding a 1/2 in my greater than sequence. So I want you to notice my actual partial sum is more than this value. And this keeps going up by a half, and it's going to do that forever. So as you can see, you can already get the feeling, hey, this is getting unbounded, because I just keep adding a constant number and it never stops. But this is more than that. It's greater than that. So this thing is getting even bigger, even faster. Not a whole lot faster, but faster than this thing. And this is going to end up being infinite. Let's go all the way. A sub 2 to the k is going to be greater than 1 plus whatever that k is times a half, right? 8 is 2 to the third, that's why I have a 3. 4 is 2 to the 2, right? So times 2. So this is the generic version of that. And if I take the limit as k goes to infinity of both sides, then the limit as k goes to infinity is infinity. Plus 1 times a half, whatever, it's still infinity. Okay? So I'll just get generic here as k goes to infinity. 2 to the infinity goes to the infinity, right? So the limit as n goes to infinity of a sub n is infinity. In other words, the limit of the partial sums would have to be unbounded, as we were seeing from the pattern here. This is unbounded, and the partial sums are more than that. So it's all unbounded, meaning this series diverges. But wait a minute. The limit of the sequence 1 over n is 0. And that's what the whole point of this logic that we're talking about here, okay? Even if this limit of the sequence that you're using is 0, that does not guarantee that the series converges. Sometimes it may happen that your series does converge, and other times it may not. So it's a good place to start. If you approach a series and the limit of the sequence is not 0, you're done. Automatic diverge. However, if the limit does equal 0, you're not done. That's a good place to start. You can feel like, this might converge. And then you move on to another method, or maybe brute force it to see what it might converge to. Just a quick visual here. If you look at the sequence 1 over n, you can see that that sequence does converge to 0 here. But it very, very slowly starts to just pick up and just take off to infinity when you have it in a series. When you actually start adding together all of those fractions, it does actually go off to infinity. It goes off very slowly now, but this final determination here is that it does actually diverge to infinity. Slowly, but it does get there. So let's finish up with a few quick examples of how I can use that last logic statement in a couple of situations, and then the other couple of situations when I can't use it and I have to re-expand. Okay, so on these two here, first thing I'm going to do, well, with any series, actually, with all 4 of them, I'm going to approach the limit of the sequence first. Okay, it's too easy to do to not just try real quick to see if it helps you just get to a quick solution of does this series converge or diverge. And remember, that's our main goal for this whole first part of the unit here is here's a series, an infinite series. Does it converge or does it diverge? And that's really the main question. So I have this infinite series here. And what I'm going to do first is I'm going to try to take the limit, especially if it looks like something that I can do quickly. Now, if it's a limit that looks like it's going to take you a long time and maybe there's another way to approach it, then you might want to skip the limit. But this one's pretty straightforward. If I do the limit as n goes to infinity of n plus 3n squared over 4 minus 5n squared, remember your old techniques, as it goes to infinity, right, these two are tied, I'm going to end up with the coefficients of those. This equals negative 3/5. Well, the last time I checked, negative 3/5 was not 0. So therefore, this particular series diverges. Because his limit is not 0, it's an automatic diverge. Next, right here, I'm going to take the limit of the sequence, right? So that would be 4 times the limit as n goes to infinity of 11 over 3 to the n. Okay, this is just an exponential limit. And remember, exponentials can go one of 2 ways. It just depends on if this is an increasing or a decreasing exponential. If it's a decreasing exponential, then it approaches 0 like an asymptote. If it's an increasing exponential, then you're on the unbounded side of an exponential curve. Okay, now how do I tell the difference? Well, the number on the inside. If the number on the inside is larger than 1 in value, then this is an increasing exponential. Well, of course, because this is a positive n right here. And it just so happens that 11/3 is greater than 1. Therefore, this limit goes to infinity, which of course, again, is not 0. Therefore, this particular series diverges. Incidentally, you may recognize the format here. The sequence is something we would have talked about in the last lecture. It's a geometric sequence which forms a geometric series. We'll talk about those more in the next lecture. Here's another one of that same kind. This is also a geometric sequence which does form a geometric series. And if I perform this limit, the limit as n goes to infinity of 1/2 to the n is 0. Absolutely it is 0. Because 1/2 is less than 1, it's a decreasing exponential on the positive side. It's going to approach the x-axis like an asymptote, which then gives me the limit at infinity of 0. Okay? So does that mean we're done? We can say, yep, this one converges. No, we cannot say that. Now that we've seen that this is equal to 0, it's like, maybe it converges. Or maybe it's like that harmonic series, and even though the limit is 0, it still diverges. I don't know. We've got to test it out and see. Right? Okay. So then, right here, I'm going to start just listing out my sequence. Right? Like we did before. The sequence here is when n is 0, I have 1, then 1/2, then 1/4, because it's going to be squared, right? Then cubed will give me 1/8 to the 4th power, 1/16, 5th power, 6th power. That should be far enough. 1/64 is pretty far out there. Okay. So let's make the partial sums. Capital A0 is 1. Capital A1 is the 1 plus the 1/2, which is going to give you 3/2, which is 1.5. Okay, then A2 is going to be the 1 plus the 1/2 plus the 4th, which is just the 1.5 plus another quarter, 1.75. Okay, then A3, I'll add in all of this, right, plus the 1/8, and I'll go ahead and save myself some time here. I have 1.875. A4 ends up being 1.9375. Okay, A5, 1.96875. A6, that's adding up all the way up to what I've got over there. A6 is 1.984375. Okay, so do you think we have a pattern here? It's definitely slowing down, right? Which makes sense. My limit goes to 0, and since that's an exponential type of limit, it's going to go to 0 pretty fast, which means this thing's going to slow down pretty fast. So it should converge pretty quickly. I'm only at A6, and it didn't jump very much here, right? It's slowing down. If you would guess 2, you'd be absolutely right. The eventual sum here, this limit, as k goes to infinity of A sub k, is most certainly 2. In the next lecture, you'll see we have a way of computing geometric series solutions if they're convergent. Okay, so this one is definitely convergent. Not because of the limit, but because we found a limit to the series of partial sums, right? Or the sequence of partial sums from the series. Okay, one more. Again, I'm going to take this limit, and of course, you're going to see that this limit is 0 very quickly. Limit as n goes to infinity of 3 over 5 to the n plus 1. And what I'm getting is 5 to the n as n goes to infinity. This is going to be infinite, right? So I'm getting 3 over infinity, which is going to go to 0. Again, all this tells me is I'm not done yet. I don't have any other method, so I'm going to just start listing out my sequence, and then I'm going to start listing out the partial sums. So my sequence is 3 over 2 when n is 0, 3 over 6, I know that's a half. I'm just going to leave it so that you can see the pattern. 3 over 26, 3 over 126, 3 over 626, 3 over 3126. Okay? And of course it keeps going on from there. All it is the numerator is 3 every time, and the denominator is just 1 more than some power of 5, right? 5 to the 0 is 1, then 5 to the 1 is 5, 25, 125, 625. It's just 1 more than the power of 5 every time. Okay? So then my partial sums, A0 is 3 halves, so 1.5. A1 is 3 halves plus 1 half, so 2. A2 is 3 halves plus a half, which is 2, plus 3 over 26. So then this is where it starts getting where I need to start chopping these things, right? I'm just going to start approximate here. A3 is approximately 2.13919. A4 is approximately 2.14399. A5 is approximately 2.14495. Okay, so very quickly you'll see this thing slows down also. It also has sort of an exponential, pattern to it there. It's gonna hone in pretty quickly. However, this is not one of those casual series that we just have a nice, beautiful answer to. It takes a rather advanced method to even approach what this thing might actually be as an exact value. Okay? For now, you need to be satisfied with a very, very good approximation. This sum, okay, this series is approximately equal to 2.145186115. I'll just do 156. Okay? But it does converge. And I didn't need to find that approximate answer to know that it converges. I can see from the sequence of partial sums that this was definitely slowing down. My first guess was going to be 2.15, right? Because it does seem to be going to that, but as you can see, it didn't get there quite. It's 2.145, and then it's an irrational number. There is not a nice, beautiful symbol just for this particular series. It's an irrational decimal, goes on forever with no pattern. Okay? But the main point is it does converge, and we do have ways of actually proving that. This is sort of a hand waving. I can see that it does converge, and then I'm giving you a good approximation, right? I know it's sort of hand waving, but we're building on the ideas and the skills here. In a couple of lectures, you'll see I have an actual way of comparing this to other things that I know to use as a proof that this definitely does converge. And as I said before, sometimes the methods for finding what they converge to are extremely more advanced for what we need to study here. Just the fact that you know that it converges is what we're building the skill for right now. Okay, so I hope these examples and ideas have shown you what we're really trying to build here. Okay, stay tuned for the next one, which is going to be on our first two very special series on geometric and telescoping series. Let's finish up with looking at these four sequences on the graph here. I've got the first one, the n plus 3n squared over 4 minus 5n squared. And remember, we determined that this one diverged, well, just because of the limit, right? The limit doesn't go to 0, and you're going to see that in this sequence right here. As I let k get to be larger here, you can see the sequence does actually start converging to a value. And it does happen to be the value of -3/5, as you can see through this line right here. Right? It does actually converge up to the -3/5 line here. That's the sequence. Now the series diverges to the negative side. You can see the red dots start to take off right here pretty quickly. And if I shrink this up, you can see it takes a lot of shrinking just to fit a lot of these dots on the screen. This thing is diverging extremely fast. It's going off to -infinity. Definitely unbounded in the negative direction. Okay. So let's get rid of that. Let's turn off these. And the next one that we want to talk about was the 4 times 11 over 3 to the n power. Okay, so here's the sequence. The sequence itself is going to be really, really large. See, there's the first dot of it right there. I have to get up into the thousands. And this is only the sequence, folks. This is the sequence that's just unboundedly, extremely increasing here. So I'm in the 10,000s up to the 100,000s here. The series, forget about it. The series is going to be even worse. If I turn off the sequence, you can see the series is just unbounded here, like enormously unbounded, very, very quickly. Okay, so let's get this back to normal here. And let's start looking at those two series that were convergent. Okay, so the first one was just the 1/2 to the n power. So as you can see, the 1/2 to the x is night and day with the one that we were just looking at. And this one does indeed actually go down to 0 for the sequence. It goes to 0, which does cause my series to converge. It's not the whole reason, but it does allow the series the ability to converge. And you'll notice it does actually converge to 2 very quickly here. The last series that we were looking at is the series where 3 is over 5 to the n plus 1. Okay, and as you can see, the sequence does converge to 0, which allows the opportunity for the series to converge. And it actually doesn't take very long for that series to converge. You can see it picks up and gets right above 2 right here. If I were to type in that number, that was the good approximation, the 2.14518615156. You can see that that this thing is converging to that actual value there. It's like centered on those points right there.